Didn't work. Oh, you're passing me this. Okay. It's happening. All right. We're doing it, guys. Okay. All right. This is so exciting. Okay. I'm Eliot Halley Vrijmoet. I am just finished my first year as a postdoc at Smith College as part of the 5-college astronomy department. And I also work closely with the RECONS, the Research Consortium on Nearby Stars. And I'm here today. I'm really excited to be here today to talk about my very favorite things. And that is when the slide advances. These work. All right. My very favorite things are the things that are moving around in space. And this is too big, so I'm narrowing it down. We're going to talk about things that are moving around stars. And for me, this encompasses, I'm going to click on the slide, like instructions. You got this. We got this, guys. This way. Yes. You turn it off. Oh, this includes stars that are moving around stars. And it includes planets that are moving around stars. No, please, it's fine. You're doing great. Now my time is it's all right. We're good. Things that are moving around stars. I like the stars that are moving around stars. I like the planets that are moving around stars. And if I remember the right direction to go on this, it's wonderful. All right. And also, these things that are not really quite stars and not really quite planets, maybe I'll just stand over here. They're cool too. I mean, they're great. All of these things, I want to do all of it. It's too much for a talk. It's too much for maybe a career, but that's all right. That's all right. We're going to get into it. What I want to know is, what are the stories of these objects? What are their histories? How is it that this process of star formation and all the things that happen after it produces this wide diversity of objects? And how does the formations of these different types of objects affect potential formations of others and their whole lives and how this works? So, I said this is too much for one talk. We're going to focus today on the left-hand side of this slide. I'm figuring it out. The left-hand side of this slide. We're going to talk about stars moving around stars. And then you might be thinking, okay, come on, this is a solved problem. We pretty much know about stars moving around stars. And you're mostly right. We know, for example, you have to point it at the thing. For example, how often these occur. As you get toward more massive stars, those stars are more often in systems with another star. But this isn't the full story. This isn't everything. Because those stars in their systems and multiples, they're not just chilling there. They're moving around their common centers of mass. And there we go. And so when you go out there and you observe a binary and you see, okay, it's got some separation. This isn't the whole story, right? There's a whole suite of potential orbits that the stars can have. You go out there and you look at it in a couple of years, it's going to be in a different place. And this is essential because this is dictating the environments around these stars. This is dictating the kinds of other things that you might care about, like maybe planets that form around these stars. And it's also important if you're going to do things like point a big fancy observatory, like, I don't know, Habitable Worlds Observatory at some binaries, you're going to want to know where the stellar companions are when that observatory launches, not where it was in 2018, the last time someone updated it on the WDS. So it's important to know these dynamics of these things. What I'd like to know then is, what is the suite of potential orbits for stars moving around stars? And hopefully, these small lower mass things too, eventually. So let's think about, what are the shapes of these things going to be? What are the sizes of these orbits going to be? And I'm going to focus today on our lowest mass stars, which now I don't need to justify because we had a wonderful talk that did it for me. Let's think about the stars at the end of the main sequence. Let's think about the M dwarfs. These are the most prolific stars in our solar neighborhood. And they're wonderful hosts for our exoplanet searches because they're just so, small and cute. They got very little mass. It's wonderful. So what I did for the PhD is I went and took a survey of M dwarf orbits. And if you go to the literature and you just pull together all the orbits of M dwarf where the primary is an M dwarf star, you might want to plot it as something like this, figuring it out. What we have here is a plot of the eccentricities of those orbits, so the shapes of the orbits against their sizes, their orbital periods. And this is only the orbits from the literature. And already we're seeing that, okay, as you get towards larger orbit sizes, they tend to be more eccentric or have a wider range. And then that distribution changes as you go toward the left-hand side, towards the shorter orbits. And then we have this really fun thing where at the very short periods shorter than about 7 days, there we go, there's this drop off and all your orbits are circular. And this is because of our wonderful friend tidal forces that will quickly circularize those systems when they get that close together. And this is interesting already because if you do the same exercise for the FGK stars, their tidal circularization period is higher. It's about 12 days. So already with just the literature orbits, we can say, M dwarfs have to be closer together to tidally circularize. That's fun. But let's zoom out again and let's talk about the wider orbits. Now, we have a lot of dots on this plot. It's good, but I wanted more. So I'm going to add to this plot a couple of observing programs. The most significant of these is the Recon's astrometry program, which began in 1999. So this year we're having our 25-year anniversary. It's very exciting. And what we do at the Recon's program is we observe this consistent set of nearby low mass stars several times throughout the year. And we've been doing this for a long time, so we have a really large data set. And we do it all from this nice little telescope down at Cerro Tololo Inter-American Observatory, the 0.9-meter telescope, the best telescope in the world. And it all happens here. We take astrometry there from those same images, we get variability, and so with a really long data set, you can get a lot of wonderful long period orbits. But that's not all. I want more dots on the plot. So I started a different observing program to supplement it. And with this, and what I'm doing here is I'm doing speckle interferometry at SOAR, which is on Cerro Pachon, which is literally next door to Cerro Tololo. And what I'm doing with that is I am targeting several hundred M-dwarf multiples and basically mapping their orbits, similar procedure, mapping their orbits several times per year. And that is still ongoing, so there should be some more papers from that coming out in the future. Now, between these two things, we have about 70 orbits to add to the plot, and now it's looking pretty nice. Yeah, we're filling it out. Now we can start thinking about some science of orbits. So, all right, what I'm going to do is I'm going to change all these dots to the same color to make it a little less chaotic. And I'm going to overlay on them the results from a really similar work study done by Deepak Raghavan in 2010 for his PhD thesis. And what he did is he studied FGK stars, or binaries of FGK stars. So think solar type stars, more massive than my guys. And now we can start to compare the distributions of these M dwarfs versus their higher mass cousins. And they're kind of similar. There's some areas where they're different. My favorite spot, as some people know, is over here in the lower right-hand corner, where you notice we have a lot of black dots and very few of these goldish orange dots. So it seems like at long orbital periods, it's these lower mass things that are more circular, and the higher mass things are avoiding this area. You can also see this if you take histograms of the distribution. So these are the eccentricity distributions for the solar type systems on the top and my M dwarfs in the middle. And you can see it's kind of more built up on the left-hand side in the lower mass stars. The trend continues if you look at even lower mass things. So Trent Dupuy and Michael Liu did a similar thing with systems 0.1 solar mass or less. And they don't have quite so many because these things orbit really slow when they're this low mass. But now it looks like as we go down in mass, the eccentricity distribution shifts a little toward the left side. And that's exciting. Okay, so what's going on there? What's different about these different populations that could be causing that to happen? And it's so complicated. There's a million different things that could be happening here, and there's not enough time to do it, especially because I messed up the tech. But one idea we can think about is what if it's just like the types of companions we have? Because our solar type friends, they have mostly stellar companions, and the ones on the bottom here are going to have mostly brown dwarf companions, and my M dwarfs are have a mix. So what if it's like the masses of what if these different types of companions form in different ways that actually impart on them a little bit different eccentricities? Well, I can get the masses, or I can estimate the masses, it's complicated, of the companions to my M dwarfs here in the middle and look at the eccentricity distributions of them. And I plotted on here some scaled up KDEs just to draw your eye, but the important thing is at the very top, we have our most massive companions, the M dwarfs. Then as you go down, they get less massive. And you notice it's kind of sketch. It's not the best. So, but we're getting somewhere because at the top, the distribution is different than at the bottom. It starts a little bit more peaked or flat. It becomes more peaked as you go down. But there's an enormous issue that I'm sure lots of people have spotted, which is the y-axes of the plots are not exactly what I want them to be. It'd be nicer if the numbers were a little bit bigger. So what do we need to do? Well, we need more orbits of these low mass stars. And in particular, we need more reliable masses. I had to estimate masses for a lot of these things. So there's a hint of something interesting happening here, but it could use some more work. All right, well, what if the situation is that it's the process of the star that brought the two stars together in all these cases? What if it's the dynamical evolution of these stars from their initial birthplace all the way down to their less than 10 AU separation where we see them today? Now, that process should impart some accretion onto the stars, and that should have some influence on the orbit. So we can think about the mass ratios of the M dwarfs, and we could plot those. Well, it's the eccentricity distribution as a function of mass ratio. Well, it's different as you go towards the twins near the top and more different stars, more different M1s and M2s at the bottom. It's not quite the same. So our ones at the bottom maybe had less accretion, and the ones at the top maybe had more accretion because they're more similar. But again, we don't have enough masses. We already talked about that. And then there's a huge issue here, which is that there's these massive observational biases baked into my mass ratios, which is really sad to say in front of all these people. But let me tell you what I mean here. As we go toward, if we look at our period versus eccentricity plots, everything on the left we get from radial velocities. They're good at some things and less good at others. Everything that's accessible to visual orbits is good at finding stellar companions, not so good at the very lowest mass things. And even the recons astrometry, this is good at most stellar companions, but not so good at the lowest mass companions. So we have some holes in the parameter space. And what I really want is this bigger picture here. And I want something that I can analyze better statistically. So what I really want is a uniform survey of all this orbital period space from the lowest, from days long periods out to decades long periods. Now there's hope here. There's hope. Because, for example, we already have one thing in the bag. We have our long-term astrometry program. It's been going for a long time. We're sensitive down to several tens of Jupiter masses. And we have about 100 potential orbits in there. So I'm working on this year. We also have our friend Gaia coming out with another data release soon. They're not going to be looking at quite so much. They're not going to have quite so much data for us, but they're going to have teeny tiny error bars. It's on there. I scaled it down. And they're going to have thousands to tens of thousands of orbits. And there's one more thing. There's more than one more thing, but there's one more thing that's I put on here. We're also going to have another survey that's going to go for 10 years, the legacy survey of space and time. It's going to go for about 10 years. It's going to survey the southern hemisphere over and over and over again in that time. And it's going to have an enormous field of view, which is actually not the best for astrometry, but I would argue that we can look at little subsets of those images and do better, get to at least what we get with the recons program. So what I want you to do is imagine for a minute the data set that we're going to have in a few years. Imagine if we had our data spanning from, say, 1999 to 2035. And imagine if we marry this multi-decade baseline with Jupiter mass precision. I mean, this is absolutely going to be covering those holes in the parameter space that we have from what I've got so far. And it's certainly going to be working towards our dream of like marrying together all these different regimes. So I hope that you're excited about this because I'm pretty gosh darn excited about it too. Thank you. What is the age? So I did my very best to get only things from within 25 parsecs. There's a few like 25 to 30s out in the set. So by and large, they're all wonderfully ancient. We have a few 200 mega year things. There's, I think, like a beta pic member that's in there that I kick out when I think about circularization. But by and large, they're very wonderfully old. Yes.